All right, here we go with part 2 of our polynomial notes. We're going to pick up right where we left off, starting with example 5. So here I've got a polynomial function. What I'd like for you to do is take this function and put it in your Inspire calculator. Go ahead and plug that in now. You can pause the video.
So here is the graph of the polynomial function. In order to see the full curvature of the graph, you may have to adjust your window size. For example, I've got mine set from y equals negative 80 to y equals positive 80, and x equals negative 10 to positive 10. Let's take a look at the zeros of this graph. We've got one zero here and another here. But that's only two real zeros here on this graph. I thought we had a polynomial of degree 4. There should be 4 zeros, right? So in example 2, we had a quadratic and we had 2 zeros. Example 3, we had a quintic, but our 2 zeros were multiplicity 2 and 3, so that's how we got our 5 real zeros. For something like this, there is no duplicate multiplicity. We're just looking at it passes through and it passes through again. We don't have any even multiplicity at either of these zeros. So what we're going to explore today is imaginary zeros. So back to the notes packet. Let's start filling in some of the things that we know. The parent function for this polynomial is a quartic. This is f of x equals x to the fourth. The degree of this polynomial is 4. That's the highest exponent. We know from our calculator that the two x-intercepts are at negative 3, 0 and 2, 0. So we can go ahead and plot those. We have one at negative 3 and one at positive 2. Okay. Our y-intercept we can solve for. We can say f of 0, this is where x equals 0, is 0 to the fourth minus 3 times 0 cubed minus 5 times 0 squared plus 29 times 0 minus 30. Of course, all of our terms that are multiplied by 0 get zeroed out, so all that's left is our y-intercept of negative 30. So we can go ahead and plot that too. We know that the domain is all real numbers, so from negative infinity to infinity. That's true for all polynomials. The range, we can find that minimum. Remember, it curved down. That minimum that was down here, use your calculator to find that minimum. We find that it's negative 70.66. And of course, the range, it continues all the way up to positive infinity. And we also want to include that lower bound, negative 70.66, because the function does hit that minimum. So sketching that, so this would go all the way down to like negative 70.66. That's right about here. We can sketch the graph. It comes up, and this curves upward, and we get this behavior here. And this should make sense. We've got a quartic, so the end behavior is the same on both ends. The leading coefficient is positive, so they're both going upward to positive infinity. So let's go ahead and write that out. As x approaches positive infinity, our function f of x also approaches positive infinity. And as x approaches negative infinity, f of x approaches positive infinity. So again, we've got two real zeros here at negative 3 and positive 2. So what happened to the other two zeros? Well, in order to find the other two zeros, right, the x values that make this equation equal to 0 true, let's solve for them. So I'm going to go ahead and rewrite the function. So f of x equals x to the fourth minus 3x cubed minus 5x squared plus 29x minus 30. We already know that we have a 0 at x equals negative 3. So using what we learned in Algebra 2, let's use synthetic division to factor out that factor x plus 3. So using synthetic division, again, we write the coefficients of each of the terms in descending order. So for the x to the fourth term, our coefficient's 1. X cubed, our coefficient's negative 3. X squared term, our coefficient's negative 5. Our x term, our coefficient's 29. And our constant is negative 30. So for synthetic division, we bring down the first term, and then we multiply these two. Negative 3 times 1 gives us negative 3. And then we bring that up here and we add these two terms. So negative 3 plus negative 3 gives us negative 6. Again, we multiply negative 3 times negative 6 is a positive 18, and we add these two terms. Negative 5 plus 18 gives us a positive 13. Negative 3 times 13 is a negative 39. Adding these two terms, we have negative 10. And then last but not least, multiplying, we have negative 3 times negative 10 is positive 30. Add those up and you get 0. And when that last term cancels out and you get a 0, that confirms that this is a 0 of this polynomial. So now if we were to rewrite this, we have f of x is equal to that 0x minus 3, that's what we just confirmed, or x plus 3, sorry. And then we've got this polynomial here. So we have x cubed minus 6x squared plus 13x minus 10. So we're just using these coefficients and we're writing them as a polynomial in standard form. But we can continue going. We've got another 0. We've got a 0 at positive 2. So at positive 2, we can rewrite these coefficients again. We've got 1, negative 6, 13, and negative 10. And we're going to use synthetic division again to see if we can continue factoring this. So we bring down the 1. 2 times 1 is 2. Negative 6 plus 2 is negative 4. Times 2 is negative 8. 13 plus negative 8 is a positive 5. 2 times positive 5 is positive 10. And negative 10 plus 10 is 0. So this x equals 2 is a 0. So then rewriting the function again, its factorization, we have x plus 3, x minus 2, those are our original zeros. And then we've got this quadratic here, x squared minus 4x plus 5. So again, a 0 of the function is the x values for which the function equals 0, right? It's our x-intercepts. So if we set the function equal to 0, right, using the zero product property, we already know that the solution for a 0 is negative 3, it's positive 2. But what are the zeros defined by this factor? Well, in order to find that, we set it equal to 0 using the zero product property. So x squared minus 4x plus 5 equals 0. And in order to solve this equation, we have to use the quadratic formula. So x equals negative b plus or minus square root of b squared minus 4 times a times c, all over 2a. And again, a, b, and c are the coefficients in our quadratic and standard form. So simplifying this, we have 16 minus 20 is negative 4. The square root is 2i. So we have x equals 4 plus or minus 2i all over 2. And then simplifying that, we have 2 plus or minus I. So we have the other two. Remember, we had two zeros at negative 3 and positive 2. We've got the other two zeros here. These are our imaginary zeros. A quick note, imaginary zeros come in pairs. Always. So imaginary zeros come in pairs. Why do imaginary zeros always come in pairs? Well, that brings us to our conjugate zeros theorem. So remember, a complex number I can write in the form z equals a plus bi, where its conjugate is a minus bi. So these are complex conjugates of one another. So the conjugate zeros theorem states that if the polynomial p has real coefficients and the complex number, and we'll call that complex number z, is a 0 of p, so it's a 0 of the polynomial, then the conjugate zeros theorem states that its complex conjugate is also a 0 of p. So an example, if we determine that, say, the complex number 5 minus 3i is a 0 of a polynomial, then this conjugate zeros theorem states that 5 plus 3i, its conjugate, is also a 0. Let's take a look at the next function here. Here we've got f of x equals x cubed minus 2x plus 4, and then I give you that f of negative 2 equals 0. If we were to plot this point, f of negative 2 equals 0, that's where x equals negative 2. We're saying that the function is equal to 0 there. So this is another way of telling us that we have a 0 at x equals negative 2. So already I can write that we have an x-intercept at negative 2, 0. The parent function for this, well, we're looking at a cubic, so the parent function is f of x equals x cubed. The degree of this function is 3, that's the highest exponent. Our y-intercept we can solve for, so that's f of 0, that's where x equals 0, is 0 cubed minus 2 times 0 plus 4. So our y-intercept is 4. So we can plot that. All right. And then we're looking at a cubic with a leading coefficient that is positive. So we know that a cubic with a leading coefficient that's positive starts off in quadrant 3, comes up and continues on to quadrant 1. So we're going to draw that cubic function. Remember, that's that S shape. It's going to come up, back down, and curve back upward. So a sketch of the graph. It doesn't have to be perfect, just a sketch of the graph. Make sure it crosses through each of these points. We get the general shape of the graph, and that the end behavior follows. The domain of this function is from negative infinity to infinity. So all real numbers. The range, is there any number that isn't hit by the function? Nope. So our range is also all real numbers. That's true for any odd degree polynomial. Our end behavior. So as x approaches negative infinity, the function approaches negative infinity. As x approaches positive infinity, the function also approaches positive infinity. So let's find the imaginary zeros. So here we've got our function, which is f of x equals x cubed minus 2x plus 4. I already know that we have imaginary zeros because we only have one real zero. We've got one x-intercept. So that means that the other two zeros of this cubic function are imaginary. So let's go ahead and find them. So using what we know that we have a 0 at negative 2. And using synthetic division, we have our x cubed term, the coefficient is 1. Our x squared term, our coefficient is 0. Our x term, our coefficient is negative 2. And then our constant is 4. So using synthetic division, we bring down the 1 times negative 2 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. Negative 2 plus 4 is positive 2. And last but not least, negative 2 times 2 is negative 4, which adding to positive 4 is 0. So then we can rewrite the function using its factorization, x plus 2 and x squared minus 2x plus 2. In order to find its imaginary zeros, we use the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac, so 4 times a times c is 8, all over 2 times a. Simplifying this, we have x equals 2 plus or minus the square root of negative 4, or we have 2 plus or minus 2i, all over 2. and we get the imaginary zeros of 1 plus or minus I. So those are our other two zeros. Let's try another example. Looking at this polynomial here, how can we determine the degree of this polynomial? Well, we can always count how many x's we have. So here we have 1x, here we have an x quantity squared, so there's 2 more x's, and then here we have an x quantity squared as well, so that's 2 more x's. In total, we have 5 x's, so our degree is 5. That tells us that our parent function is going to be that this is a quintic. Our x-intercepts are zeros, are real zeros. So we've got a 0 at x equals -2, so we can plot that. We've got a 0 at x equals 1. And we have a 0 at x equals +3. So we can go ahead and write those as our x-intercepts. We have 1 at -2, 0. We have 1 at 1, 0. And 1 at 3, 0. To find the y-intercept, we can solve for. We can plug in 0 for x. So we're finding f of 0, which is -4 times 0 plus 2 times 0 minus 1 squared times 0 minus 3 squared. So we have -4 times 2 times, that should be +1, and then times +9. Multiply -4 times 2 times 1 times 9 gives us -72. So we've got a y-intercept of 0, -72. So we can plot that. That's all the way down here. Okay, let's sketch the graph. So we've got, it's a quintic, so the end behavior is going to be in opposite directions. And our leading coefficient, that number out in front, is negative. So instead of starting low and ending high, we're going to start high and end low. So we'll start up here. We're going to cross through our first 0 at x equals -2. That multiplicity is 1, so we're just going to pass through that. It's going to come all the way down through the 0. It's going to come down and cross our y-intercept. And now we're approaching our next 0 at x equals 1. This has a multiplicity of 2, so we're looking at a bounce. It's going to come up, it's going to hit that 0, and it's going to bounce off. We got to come back around and hit our next 0 at x equals 3, and that one has a multiplicity of 2, so that bounces as well. And then we continue onward. So I always double check that our end behavior still makes sense. We've got a quintic, so the end behavior should be going in opposite directions. So it looks like we've got that here, and then the leading coefficient is negative, so we start high and end low. So this checks out. The domain of this function is from -infinity to infinity. It's all real numbers. The range, we hit all real numbers as well. The end behavior, as x approaches positive infinity, what happens to our function? So as we increase x, our function decreases. So our function approaches negative infinity. As x approaches negative infinity, what happens to our function? It's increasing. So f of x approaches positive infinity. How many imaginary zeros do we have? Well, we've got 1, 2, 3 real zeros. But the truth is we don't have any imaginary zeros. Why don't we have any imaginary zeros? Well, let's take a look back at the equation. We've got 1x, we've got 1 0 here. We've got 2 x's here. This 0 at x equals 1, if we were to expand this out, we would have a 0 at 1 and then another 0 at 1. Because the multiplicity is 2, we're counting that real 0 twice. The same is true for the 0 at x equals 3. So let's go ahead and write that out. The zeros, 1 and 3, have multiplicity 2. So we count those real zeros twice. Go ahead and try this next example on your own. You can pause the video, work it out, and then when you're ready to check your answers, hit play. Alright, go ahead and check your work. For this polynomial here, we can factor this by grouping. So I rewrote it and used parentheses to group my factors. I factored out GCFs and got down to this here. So this tells us that we have a 0 at -2 and a 0 at +2. And the 0 at +2 has a multiplicity of 2. We've got a cubic function. The degree is 3. Our y-intercept is 0, 8. Our domain and range are all real numbers. And as we sketch the graph, of course, we pass through the 0 at -2. We come up, hit our y-intercept. And then at x equals 2, we've got a bounce. The multiplicity is 2. That goes off. Our leading coefficient is positive, so our end behavior for a cubic is that it starts low and ends high. So as x approaches -infinity, f of x approaches -infinity. And as x approaches +infinity, f of x also approaches +infinity. We don't have any imaginary zeros because we count the 1 here and the bounce here. That counts for all 3 of our zeros. Our 0 at x equals 2 has multiplicity of 2. So the last thing that we're learning today is, given a graph, see if we can find the equation. So using what we know about the graph, multiplicity, bounces, things like that, let's see if we can write an equation for this. I know that we've got our end behavior is going off in opposite directions, so we must have a degree that is odd. I also know that we've got a 0 here, 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 and here. But this one here, I notice that we have a bounce. So this 0 is counted twice. So we've got 1, 2, 3, 4, 5. So we can say that our degree is 5. And that makes sense with our end behavior. It's going off in opposite directions. You might also notice immediately here that our leading coefficient is going to be negative. But let's go ahead and find that. So we can start writing the equation. F of x equals our leading coefficient. We don't know what it is, so we're going to say that's a. Because we can always take this graph and we can stretch it vertically. But we're going to find our leading coefficient using our y-intercept. So using our zeros now, we can write its factorization. So x plus 5. We have x plus 1, x minus 1, and x minus 9. And that quantity is squared because we have a bounce. We also know, in order to solve for a, we can use our y-intercept. So we can say that f of 0, which is where x equals 0, our y-intercept is 2. So f of 0 is 2. Well, we know that's where x equals 0, so we can substitute in 0 for x in our equation. So we have 0 plus 5, 0 plus 1, 0 minus 1, and 0 minus 9 quantity squared. And here we've got an equation with one variable we can solve for a. So we have 2 equals a times 5 times 1 times -1 times 81. So multiplying that out, we have 2 equals a times, this would be -405. So then our leading coefficient must be -2/405. And that should make sense because we've got a degree 5 polynomial where as x approaches -infinity, our function approaches +infinity, and vice versa. So writing out our full equation, we have f of x equals our leading coefficient, -2/405, and then all of our factors, x plus 5, x plus 1, x minus 1, and x minus 9 quantity squared. We could expand this out, but its factorization is perfectly fine. Let's try another. So looking at this one here, I notice that the end behavior is going off in the same direction, so we're looking at an even degree polynomial. We've got a bounce at -4, and we've got a bounce at +7. Those are our only 2 zeros. And we're counting each of these twice, so we can say that we've got a polynomial of degree 4. So writing out the equation, we have f of x equals, well, we've got our leading coefficient, which we don't know yet, a, and then times, let's use our negative 4, so x plus 4, we've got a bounce, so that quantity is squared. And then we've got x minus 7, we've got another bounce, so that quantity is squared. We know that our y-intercept is 15, so we're saying f of 0 equals 15, which is equal to our equation where x equals 0. So 0 plus 4, quantity squared, and 0 minus 7, quantity squared. So solving for a, we have 15 equals a times 16 times 49. So we get that a equals 15 over 784. So that's our leading coefficient. And it's positive. That should make sense. A degree 4 polynomial, both ends go up to positive infinity. So writing out our equation, we have f of x equals our leading coefficient, 15 over 784, times each of our factors, our zeros, x plus 4 squared and x minus 7 squared. Okay. The last thing that I'd like for you to do is just to answer each of these true or false questions, just as a quick knowledge check for yourself. So give these a try. You can pause the video and then we'll check your answers. All right, you can check your answers. For the first one, we need to have both the zeros, right? So we need 2 minus I, and we also need its complex conjugate, 2 plus I. So those two zeros plus this zero implies that we've got at least a cubic function. So this is false. This here is not a third degree, it's a fourth degree, right? We've got one x here, we've got two x's here, and then we've got a fourth x here. So we've got 1, 2, 3, 4. So this is a fourth degree polynomial. A fourth degree polynomial has at most 3 turning points. So remember, the shape of a fourth degree polynomial is kind of like that weird looking W. So at most it's got 3 turning points, or 3 local max or mins. A function can have more than one y-intercept. That's false. That contradicts the definition for a function. Remember, for any x, it must have a unique y. A polynomial function of even degree can have no real zeros. That's true if you were to have a function that is entirely positive. So here's a fourth degree that is where its range is entirely positive. However, an odd degree, remember the end behavior goes in both directions, so it must at some point cross the x-axis. So it must have at least one real zero. If x approaches both positive and negative infinity and the end behavior of the function is the same, then we're looking at an even degree polynomial. Okay? We're going to get a whole lot of practice on this. You can study up and have a great day, everyone.